Welcome back, everyone. We're now currently in week 6, so definitely moving through the course. Sorry for the delay to the folks who are with the Pocatello Testing Center, including the Idaho Falls Testing Center. I'm assuming that they were pretty overloaded last week since they haven't got caught up with scanning those exams and sending them over. I'm hoping they get that done soon, and I should have them graded around Thursday-ish, if they can get those in by that time. But I'm going to try to grade them just as soon as feasibly possible. I don't like going so long with stuff ungraded like that. Aside from that, where we're at so far is finishing off section 8.1, moving into section 8.2 next on surface areas. And this is our chapter on applications of the integral, but you might have noticed that this is a mathematical application. We just purely looked at the length of a curve. Same with this one. This is another mostly just mathematical application. We're only looking at surface areas of functions after we rotate them the right way. But in section 8.3, we'll look into specific applications to physics and engineering. We'll be looking into centers of mass as well as hydrostatic force. So it'll be kind of fun stuff. So 8.3 is going to be our more practical side of applications, I'd say. After that, we'll be moving into chapter 9, looking into differential equations. We have just the right knowledge to make some decent headway into that without having to jump into a real differential equations class. We can handle a lot of differential equations with where we stand now. So that's where we're at so far, folks. Any questions whatsoever before we get started today? Okay, well, let's get going. So section 8.1, we did the main problems, like the problems that you would be doing pretty much in the homework assignment. And what this section was really based on is, again, finding the length of a curve. Just a reminder of how all this goes down. We did this one derivation only because it really connects well with the major idea of chapter 8. Pretty much every good application starts off by doing something like this, finding a limit of a Riemann sum, which you can turn into a definite integral. So what we did was we took a curve that went from P0 to P3, broke down different line segments according to the partition on the x-axis, and measured that distance there. The way that distance works in the derivation is the difference x0 to x1 is just a delta x. But the tricky part about all this is you also have to use the mean value theorem to take the part in blue, find the value here through the mean value theorem, and that produces a delta x a second time. Delta x factors out, and we got to this lovely formula, which we used several different times. To make that formula work, the algebra is very, very picky. So if you feel like you get stuck on something, don't hesitate to email me about it or jump into office hours. I'll be really happy to help out. For example, just looking at a quick one here, when we're finding the length of this curve, y equals x cubed thirds plus 1 over 4x, doesn't look like it'd be too bad, but it's mostly algebra if you really look at that. First thing you have to do is calculate dy dx. We went to that quantity. Then we raised it to power 2, so we expanded it out, ended up here. Well, step 2 was raise it to power 2 and then add 1. Once we added 1, we observed that that actually factors in a nice clean way, which is really totally surprising sometimes if we're not expecting it. We got x squared plus 1 over 4x squared. So now when we put that inside the root, we have a nice cancellation. We just get to finding the antiderivative of that, and the rest of it is not so bad. So pretty much all these problems go in that kind of way. Some of them are a little bit trickier than others. Surprisingly, though, something like this gives you a factorization where you went a fourth of y into a half root y, so still factors in the same kind of way. In fact, you should feel like there's deja vu when you're doing this problem, since the algebra, although it looks different, is almost entirely similar in this way. After that, we did one with a more built-up function. Actually, this was the easiest problem in the whole set because of that identity there. 1 plus tangent squared became secant squared x. So trig identities like these are still used just left and right all over the map. Always be on the lookout for them, especially those identities in the trig substitution table from exam 1. Those are some of the major ones that keep coming back. So that was a little rundown of the problems that we ended on with Thursday. Any questions with any one of those folks at the moment? Okay, then beyond here, again, that was our main work, but this is where the notes started to take a slightly weird, different journey. The reason we're doing a little bit of this is just to connect the notes from section 8.1 in 8.2. And the notes in section 8.2 has some really weird formulas like that right there. We need to describe what we even mean when we say ds. Our author uses these differentials left and right in chapter 8. So that's part of the reasons why these notes keep going, to try to explain what's going on in section 8.2. So it's a fun, nice, relaxing problem. Just a review from Calculus 1. We take a continuous function on a closed set like this, automatically the integral exists. But we can do even better. You can define a function in this way. G of x is the area under the curve from a up to a value x. We call this an integral function. These functions are used a lot in probability, so they're more practical than they would seem on first glance. So we have to have a good handle on these things. And in fact, this is what the fundamental theorem gives us right away. That function is differentiable, and its derivative is g prime of x equals the integrand f at x. Notice there's a bit of a conflict notation when you write this all out. X had to be here because we're integrating from a to x, and x is also the input to the g function. However, you could have put x here, and you could have said dx, but it becomes a conflict of notation because x now has two meanings. For that reason and that reason alone, we just convert to variable t and write out dt. That's completely legitimate since you can always say that the integral, say 0 to 1 of x cubed, dx is the same as the integral from 0 to 1 of t cubed, dt, and so on. The actual variable doesn't matter. Sometimes this is t is called a dummy, kind of a mean name when you think about it, dummy variable. In a sense, it's just a placeholder. It's anything that's going to work out in the problem. X is also a dummy variable in this sense. It could have been anything. But the moment we have an x here, we switch to a totally new variable t just to avoid that conflict. If you forget to do that in your work, it's not major, but your work just starts to look weird because x can have two different roles all of a sudden. So let's give this a try then. We have a function, g of x is a definite integral from 4 to x of the square root of 1 plus t cubed. I don't think I could solve that on my own. T cubed is an awkward value to have here. There might be a clever way, but I'm not seeing it. But the good news is we're just evaluating g prime of x. So here's how it goes. G prime of x, if you like Leibniz notation, you'd be saying it's the derivative with respect to x of the integral function that goes from 4 to x, root 1 plus t cubed dt. This step in the middle is not required, but it's kind of cool because it's a way to think of integration is an inverse process to differentiation, the d by dx. We have a type of cancellation, and what we get as a result is f of x. F of x is what goes here, but that has a dummy variable of t, so that's confusing. When we go to write this out, it'll be square root 1 plus x cubed. That's literally all we do on that. There's no chain rule here unless there's some other function like sine x on the upper limit of integration. We just write out the integrand with the original variable x. Well, any questions about that so far, folks? Kind of weird. It's kind of weird how this is the fundamental theorem of calculus part 1. You'd think this is the theorem we use most often. No, we use most often part 2, really. But part 1 is used to actually prove part 2, so they're all just interconnected stuff. So let's get back on track then with what we're doing in these notes. We have a function that goes like, or excuse me, an integral that goes like this. We integrate from a to b, that's square root 1 plus f prime of x squared dx, and that's the length of the curve that we're describing. But just like how this is the area from 4 to x, we could say, what about an arc length function? Like this one, Sx. So Sx says integrate from a to x, that function there. Looks really familiar. In fact, if we said S of it's going, there we go. If instead of Sx, we wrote S of, let's say, b, That's where the domain ends for the function y equals a of f. For the function y equals f of x, rather, we'd be looking at this. Integrate from a to b, root 1 plus f prime. We can now say x on this because there's no conflict of interest or no conflict of notation, squared dx. But then that's just the length of the entire curve at that stage. So what is this function doing? Well, you can think of it as the length so far as you go from a to some other value, x naught, where x naught is in the middle. So just a really quick picture on that. Let's say a and b are over here. X naught is some other intermediate value. We need a continuous function on the closed set. In fact, this even says more. This is saying the derivative is continuous as well, allowing the mean value of the theorem to work and such, allowing that to be integrable. So our curve could do something like this. And we would say that S of x naught is the length of the curve y equals f of x from a to x naught. So it'd be referring to this length right here. So that's our arc length function. I don't have any direct questions really based off this kind of information. There's like 1 or 2 problems that could be assigned, not a lot of support on it. But what we really want to do this thing is find its differential. Any questions first? Okay, differentials are one of those things where we do all the time, but if you change the context of when you do the differential, it suddenly feels just really different. So if we want a differential of that thing, let's first just write it down below here to keep our eyes on the right spot. We're going from a to x of root 1 plus f prime. We have to now say t because x is in the upper limit of integration, and we'll convert to dt. But now if we take the differential of this, it goes like this. The left-hand side is ds. Over here, we have to differentiate that function, and that'd be using the fundamental theorem of calculus part 1. Let's write this in a sequence of steps. It would go like this. d by dx of the integral function from a to x, root 1 plus f prime of t squared dt. Because there's a differential, something goes over here as well. It's not dt, it would be dx. That's the variable upon which we're integrating with. So we put a dx out here. It's kind of odd when you write it all out like that. Does that make sense so far? Okay, so just a quick reminder, if y equals f of x, then the differential is dy equals f prime of x dx. So this is like the dy. This is playing the role of the f prime of x, and that's the dx on the far right end of that differential equation there. So one last step. If you take the differential, then fundamental theorem of calculus, like we said, differentiates that part automatically for us. ds becomes square root 1 plus f prime of t squared dx. So that's a kind of a nice equation. When you take more and more calculus, you'll find that these kinds of weird differential equations show up more and more and more. In calculus 1, it's in u substitution. Calculus 2, all over the map. Integration by parts uses 2 differentials, for example. Any questions at the moment?
So how about the lower and upper limit of these don't apply those, plug those into the function?
Down here?
Yeah.
Not if we're looking at the differential. Yeah, once we go to the differential, the lower and upper limit of integration are just vanished at that point.
You want to find a value and you plot this.
Yeah, absolutely. So if we want to actually work with this differential, it gets used over here for that surface area. But here's what the author mentions. We can say, therefore, the length of the curve is going to be integrate from a to b. If we want the total length of the curve, and we put in ds. So that is now the length of the curve. Our formula becomes massively compactified because ds is the right thing that would go there for the real formula. Question up here, sorry. Therefore, yeah, thanks for mentioning that. Let's define it here just to be specific. Therefore, I don't know who I picked this up from, but I just noticed people start stacking dots for their conclusions, so I started copying them as well. Oops, sorry for the scroll. It would be pretty much up to you, because once we start putting things in, if you put in, or hang on, good eye, that was my mistake right here. When we go to differentiate this, we're differentiating with respect to x. That should have been an x there. That was my mistake. So it should have followed this process. No matter what the dummy variable is, if the function is an x, your result upon differentiation should have been an x. That was my mistake there. So that one was correct with the x cubed, but thanks for spotting that. That should have been an x right in that location. Did I answer your question as well about that, Rajab, about the limits of integration? Gotcha. Other questions so far? Okay, obviously, this formula is of limited interest, right? Because if you're going to use that formula, you have to plug that back in right away to that location, and you're just back to the original thing. Only reason we did all this extra work right here is because, well, sorry, my thing is scrolling all funny. It's like the cursor forgets where it is. There we go. Oh, it's because I'm at the end of the document. Microsoft is weird with white space. So again, this formula is of limited value, but we're using it in section 8.2 just to explain some of the other formulas we're going to see in those notes there. Any last questions at all then, folks, before we take a look at surface areas next? Okay, so we've got lengths of the curves. After that saves, that takes a minute. Now we're converting over to surface areas. Well, specific kinds of surface areas. Just like in Calculus 1, in Calc 1, computing volumes is not an easy thing to do, but in some limited cases, you can make it work with cross sections or volumes of revolution. Here, we're only looking at surface areas when we revolve a curve around either the x-axis or the y-axis. So here's the setup so far. Let C be a smooth curve defined by y equals f of x. I mean, already that's pretty dense information. This right here means f prime at x is continuous. We need that for the derivation, just like we needed it for the derivation section 8.1. But another way to think about it is, if you're going to integrate that function, that's the area, that's the formula for the surface area, you have to have dy dx, that's f prime of x in Leibniz notation, actually being continuous because it guarantees the integral exists. So that's part of the reason that condition's there. We want f to be a positive function. That seems restrictive, but there's a reason for that. We're going to rotate about the x-axis, and we just want to focus on one branch. We'll start plotting what this would look like. With a warning, I'm not great with 3D sketches, so you have to use your imagination a little bit with this. We'll do the best we can. I want a positive function that goes from A to B. Doesn't have to be anything too wild. Let's just let it do that. Increase gently. The curve C is rotated about the x-axis. That's why we're focusing on the curve being positive. It's just to make the formula pick a certain direction. We're focusing on that curve, rotate about the x-axis, and we get this other part of the curve. Imagine that's a perfect mirror image. Well, we generated a surface as well. Imagine this is really in three-dimensional space. This is a line of infinitely many points, but as it rotates, it's generating infinitely many more lines at the same time. And this is the picture that emerges. I try to make it three-dimensional. I'm not sure if that would make sense based on your view. I think from here, you'd have to go dashed. That's going to be the part you can't see. Or would it be the part you can see? Would be bad at drawing these. Let me try again. Yeah, it's hard. I don't really know my perspective with these things. It looks like I have a strange object. Maybe something like that. Here's a part where we use our imagination. So we want the surface of this thing. What we do is we pick a value x. Use a different color green here. That's going to give us a line segment that goes up. That entire line segment also rotates. And what we want here is the circumference. Let's make this come out a little bit more. This is really just a circle. If we were looking at the x-axis down on it, x is right in the middle. We have a height of this thing. The height is the curve, y equals f of x. That turns into the radius on this diagram. Then the circumference will be 2 pi f of x. Or if you prefer just calling f of x y, you call it 2 pi y. So that's what this part is right here. We're not doing the full derivation since that takes a whole lot of time. But it's good to see how this comes together. You want a circumference right here to make this work. And then that part right there, that's just inherited from the length of a curve. In fact, the derivation of this thing is pretty similar, except we're doing surface areas. That entire formula carries over from section 8.1, which means the differential could be part of this as well. So that's how this kind of comes together to a nice formula. Very similar to what we've been working on. That's nice. And it turns out that extra variable y right there makes these integrals a little bit easier. There's a little bit more to this story. Your curve could be described as a y equals f of x, and that would work just fine. But if you have a different description, if x equals g of y is just a better way to describe the curve, then notice not too much difference on the formula, except you have to have a dy right here because you're integrating with respect to y. You have to change your limits of integration because that's for a y variable. But you'd still have the same curve that looks like this. It would just be x equals g of y instead of y equals f of x. We're still rotating about the x-axis, and so that part is completely similar. It's kind of nice about the formula. So we use the same exact formula, except change the limits of integration, put a dy here or a dx, based on just how your curve is described. I have one in the homework and one of these notes where x is the dependent variable, and others where y is the dependent variable. This is the more routine problem. Well, any questions so far, folks, with the description of the formulas? Yeah.
And then formula we're gonna get that describes what the curve we have, it's gonna go in that dy dx spot.
Yes, absolutely. So whatever that curve is, that's a good one for the highlighting. Thanks for mentioning that. That part right there came from that description, and dy dx comes from that description of the curve. So absolutely. However it's given is how it's inputted into that derivative there. Other questions so far? Okay. And I'm not sure when I typed in +6, let me take that off. One observation you might have made though is there's more than one way to rotate your curve. This is a rotating about the x-axis, but you could rotate this whole thing about the y-axis. So they were mentioning here, both of the formulas can be described in this way, where we saw in the prior notes, ds is square root of 1 plus, it's either dx dy or dy dx, depending on the curve. Let's put it dy dx, the more typical one, squared dx. So that's what's happening with the ds right there. I feel like maybe pencil is a better way to convey, or we'll run out of colors to highlight with. So what's going on with the y-axis? This is the formula our author gives us. But honestly, ds is nice. It's important to think of these differentials, especially in Calculus 3, where there's even more of them to consider. But for practical purposes, if you're just doing surface area, the better formula is just to write this out. You're going to be integrating from sum a to sum b, 2 pi x square root 1 plus, it's either dy dx or dx dy. That's the more typical one, like we'll see in the homework problems. But notice there is a big change this time. It's 2 pi x, not 2 pi y. Let's draw just a quick diagram to show what's happening with that. So if we're going from A to B, let's just make this a really simple curve so it's not as hard to draw. But now if we're rotating about y-axis, we're going that way. So we have a mirror image produced in this way. Here's y equals f of x and a supposed mirror image on the left. So let me just try to pretend I'm an artist for just a moment. Here is, oh wow, that's not a perfect mirror image. So that's like the back end of the surface. This is the front end. And we want the total surface area of that. Well, if you're doing this, your x right here goes between A and B. I want to highlight that in green rather. Once you pick that x, it produces a point up here, up to right here, and that whole segment rotates around in that kind of way. So we have a circle kind of going like that. Just like before, we can ask, what is the circumference of that circle? We looked at it from the y-axis going down in three-dimensional space. It would look like this. The center corresponds to the origin right here, and the length this time is the distance from here to here. It's just x for the radius. Does that make sense, visualizing it that way? So that's the weird thing that's happening on this diagram. If the radius is x, the circumference is then 2 pi x. That's why you see 2 pi x on this formula, also here as well with the differential put in ds. So there's really just two kinds of cases. About the y-axis, you're going to be using a formula like this one with either dy dx or dx dy. But for all other rotations, say y-axis, you do a formula that goes like this, 2 pi x instead. So our goal in these notes is do several problems looking at the different situations that come up and to support the homework. The homework, I'll have one about the y-axis, I'll have one that goes like this, and several that go like this, more of a routine problem. These would be the more routine problems you can expect on an actual timed exam. The rest are just more interesting cases that could come up. Any questions at all, folks, with visualizing how the formulas come together?
The top one, the rotation across the x-axis, the C and G, are they from the all the way from the down to the top, or just the positive part of the diagram?
It would be from the positive part of the diagram, yeah. So if we're using x equals g of y, the c would have came, oh, let me try again. The c would have came from here up, and the d would have came from here on the limits of integration. Because of the dy, c and d have to be constrained between your y variable now. So now your y is going somewhere in those locations.
So the A, T, and G are going to the definite points of the integration. Those are the edge of the object, and the y, the x is the radius.
So, sorry, what was that last part?
Y and the x.
Yes, absolutely. So that would be the radius on this one is y, or f of x. I should have put here just for clarity, y equals f of x on that one. But if you rotate this way, radius is just x this time. Other questions about that? Okay, putting it all together, really it's not too bad of a process. Here's what the actual problems look like. Because I'm such a poor artist, I took this book, University Calculus by J. Haas, however you say that, second edition, and he's got some pretty good graphics in there. So this is not a typical problem that you'd see on an exam. Exam problem could look like this, where I might include a plot if that's just necessary to kind of visualize how it goes together. We'll put the plots in on these as we're doing our own problems. But think of this one as kind of a warm-up. Their picture is already provided as a freebie. We're taking the curve y equals 2 root x. That's this curve in blue going here. From x equals 1, so 1, 2, to x equals 2, that's the second coordinate 2 root 2. And we're rotating the whole thing, that part of the curve, about the x-axis. It produces this band. And you can imagine that's something important. It could be the piece of something you're putting on the Chernobyl reactor to try to stop the radiation from leaking out. Who knows what this is for? If you're doing that, you'd want to know how much surface area you have to paint on that thing to warn people to stay away. So a pretty practical problem. To get the surface area, it's actually not too bad of a process. Surface area would be, take a look at what your x can do. Your x is out here, it goes from 1 to 2. I mean, it's spelled out here as well, but it's good to look at how it's presented on the diagram. That means we're taking a definite integral from 1 to 2 of 2 pi, and this is either x or y. But if you're rotating about the x-axis, it's the opposite coordinate, y. That's a way to kind of come together as a mnemonic, good way to memorize it. Rotate about the x-axis, plug in just a variable y. And sure, you could put ds in here, but in this section, if all we're doing is surface areas, better just to put in the total thing. 1 plus dy dx squared dx. So that's our problem to solve. Like before, the algebra is finicky. It's not as bad as section 8.1, but we still want to do this in a really methodical way to get it to work out. So, like before, let's start off with this part. The portion inside the square root or the radicand. I usually like to go in stages. So let's take dy dx to start. Starts off as a constant, 2 times root x. So by the constant multiple rule, it'll be 2 times root of x differentiated is 1 over 2 root x. So this just turns into 1 over root x. Now we square that thing. Might as well do it on this line. Let's suppose we were squaring it all along. And we get 1 over x. Nothing much more to say there. Now we're going to expand over and go 1 plus dy dx squared. That's just a 1 plus 1 over x. And you could square root it as it stands, but sometimes it's a good idea to do just a little bit more with it. I would say it's a clean approach to find the least common denominator. It's x. And go x plus 1 over x. So that's what's going to be in blue. You have to square root this thing. So let's imagine we were doing it all along. Square root here, here, and here. And by properties of radicals, this is really just exponent properties. You could take the root of x plus 1, divide by the root of x. So that's probably how we would approach this one. There's a lot of different ways to do it, but I feel like the cancellations are cleaner this way. Any questions, folks, to that stage? Oh, this right here?
Yeah.
That was from the derivative of the square root function right here. Whenever you differentiate that thing, you could always say it's x to the power, say, 1/2. Then it kind of goes like this weird pattern. 1/2, e power is negative 1/2, which means you can take it and drop it down to the denominator. Let me not forget the constant first. So we get 2 times x power 1/2, but you could just write it as 2 times square root of x in that way. So it's kind of an interesting little game with square root. It always does that pattern, drops it on to the denominator and doubles it. Other questions so far? Oh, for that one, what I did was promote the 1 to just x divided by x. Now we have the least common denominator across those two fractions. So we maintain the common denominator and just add across the top. So think of that one as just x over x for the addition there. Other questions at the moment? Okay, well, that's usually the most algebra, working out this, getting into the right form. Now we have the whole root right here becomes that. Might as well just expand our highlighting there. So all of that is calculated below. And we can now say, let's bring in the therefore, because we did a lot of algebra. Now we're connecting the dots from the main formula and the algebra. The surface area is a definite integral multiplied by 2 pi. We can pull that out right here if we'd like. Goes from 1 to 2. We have the function y, but because this is dx, that's not considered a variable. It's the whole function, 2 root x. Let's highlight that in yellow just to show where it came from. Then it multiplies that thing, which we simplify to root x plus 1. Let's use blue just to convey the substitution there. Root x plus 1 divided by root x. dx. So now at this stage, the root x's just cancel right off, and we have a pretty nice integral to run through. There'll be 4 pi from 1 to 2, x plus 1 to power 1/2. It's just easier for me to visualize the antiderivative in that format, aside from the square root. And we're now in business. Any questions, folks, before we finalize this answer? Okay, so next steps. Carry in the constant of 4 pi. A little bit of space. Antiderivative of x plus 1 to power 1/2. Bumps it up to a power of 3/2. That tells us to multiply by 2/3, the reciprocal, and evaluate from 1 to 2. So far, I've got an 8 pi over 3. With the evaluations, this turns into 3 to power 3/2 minus 2 to power 3/2. And we did it, folks. That's the exact surface area of this weird little band thing, whatever it happens to be. You can imagine it's something important, like it's going over some kind of nuclear reactor meltdown, maybe Fukushima or something like that, to try to keep people away and contain the radiation. So this is a totally fine answer, but the book often does this. 8 pi over 3. Let's explain just with some exponent surgery what the book often does. 3 to the power 3/2 could be visualized as, first let me make a good exponent there. That's the square root of 3 cubed. And you could say that that's 9 times 3 square rooted, which becomes 3 root 3. Our book does this a lot. This comes up a lot because for doing distances or surface areas, the square root comes up, which means you'll see power 3/2 pretty often. So I'm totally fine with that as an answer. You don't have to change it, but if you're matching up problems in the back of the book, that's 3 root 3 minus, same game on this one, 2 root 2. Totally up to you how you want to finalize your answer. It's a stylistic choice, in my opinion. We did it, folks. That is the exact surface area for this quantity here. So you could go to Sherwin-Williams, find out how much paint you have to order, depending on what that object is. We didn't actually have units on that, so that could be a long phone call. Yeah. Well, any questions, folks, with how the process goes? I agree with you. What's really crazy about this is the derivation is about finding surface areas of portions of triangles. It's a pretty clever one. So if you have the time in the reading, you don't have to read the derivations in depth, but it's so similar to section 8.1 derivation, I think it's a good one to even skim through, see how it goes. It's a pretty clever trick. Essentially, they take this picture, just like we did before, rotate the blue line segments across like that, and find the surface areas by just direct computation of all those segments, which are just portions of triangles essentially, or cones is the better word to say it, portions of cones. So extending in this direction, here's where it gets a little bit weird. Still rotate about the x-axis. So our formula isn't too different, except that that's a pretty weird curve. I feel like this would be an almost unfair exam question without a little bit of graphics to support us. And if you're really great at plotting these things in the XY plane, that you could do it by hand, I find this is a really powerful tool even for this context. So if you put in the curve with x written this way as a dependent variable, in Desmos, it still treats it as an independent variable, and this is still going to be the x-axis. That's the actual picture we really want. So just type it in as you see, x equals 1 plus 2y squared. You don't have to do this on your homework, but any extra thing you can do to visualize the problem is well worth it. You don't want just the function, you need the domain on the y variable. So let's also put in curly brace, 1 less than equals y, less than or equals to 2. Now we definitely have a picture here, but my axes are a little bit strange. Let's fix that. On the y-axis, let's go from negative 0.5 or negative 1, just to give a little bit of separation, negative 2. Here we can go up to 1, maybe 5. That does the job. So that's a more decent looking graph. Again, for a lot of these questions on a real exam, I would provide these graphics because knowing what the graph looks like can help us connect the dots of what the formula really is. So here's our graphic. Exactly, good call. We're going to have a formula that goes, oh, S goes from, well, the limits of integration are not 3 to 9, whatever those are, because if our curve is specified this way, we use those limits of integration. We're going from 1 to 2 pi y still, because of what you said, this is still a powerful mnemonic. But now this portion is also different, square root, 1 plus. We have to say dx dy this time because our function has x as a dependent variable. So dx dy squared dy. So that's what it would look like. Rotating about the x-axis will give us a picture that looks like this, schematically without drawing too much. Oh, this is the better way to draw it. We pick a variable y, it's going to go between 1 and 2. So here's a variable y. It connects with some point over here. And this whole thing is going to rotate following the direction of this rotation. So that's a radius or a height of y if you made that rotation happen, because that's the height of y right here. So that's where the y comes from in this formula. Even if it's specified in this way, still just y. Kind of surprising in a way. Any questions so far, folks, with the write-up at this stage? Okay, so the homework questions are going to look like this. I mean, they're just right out of the book. It's up to you to use your favorite technology to visualize it, or you might feel like you don't need it that as much. I'd still encourage you to do so, because on a real exam, it'll look like this. You'll have the graph. You won't have the special marks we put in ink, but you'll have the graph of the curve, just in case that's helpful for visualizing how this formula gets put together. Now we're ready to just start calculating this all out. We can start with finding this value here, like before. So let's start with dx dy. That's pretty quick. It's 1 plus 2y squared. So dx, derivative of the x function with respect to the y variable would give us 0 to start, plus 4y. So just 4y altogether. So that means if we go up to the next step, bump that to power 2. We're now dealing with the 16y squared. Add 1 to that, and we have the following. Root 1 plus dx dy squared is the square root of 1 plus 16 y squared. That's unfortunate in a certain sense because I have no algebra trick whatsoever to simplify this and eliminate the root. There's nothing. It's all because of that plus. If this was multiplied, you could take the root of 1 times the root of 16y squared. But algebraically with a plus, everything's messed up. I don't have any factorizations or any other neat trick to simplify that. But here's the miracle right here. If y appears, u substitution's on the table for us. This time, y is a variable. Let's compare that with the last problem. In the last problem, this y is a function. So although the formula looks the same, the way we actually use the formula is significantly different. Here we put in the actual function 2 root x. Here, it just stays as a variable. But actually that's good. That allows u substitution to work out just fine for us. Well, it's because of the dy right here. If there's a dy, it indicates just a variable in that case. As opposed to the other situation, if it's a dx and you throw in a y, we're safe to assume y is a function of x now. So we throw in the entire function instead. That's a really good question about that. Sorry, say again. Sort of, but if it's a two pi x, you might be thinking of that formula right there, which would imply rotation about the y-axis instead. So I think you're meaning like if you put in an x itself, it means you're putting in the function. Is that how you're meaning?
I guess maybe it's wide.
Yeah, down here with the dy means that's got to be a variable y versus dx means you have to throw in whatever the function is, which would be horrible because if this is a dx, then you have to come here and actually solve for y now. I mean, it's not horrible, but the setup of this is not supporting that at all. You'd have to do extra work. Oh, no worries at all. If there's this right here, it means your y values are going from 1 to 2, and that alone would tell you it's got to be a dy because you have limits of integration for the y variable. So that would be a good way to think about that one. These are all really good questions, the right questions you'd want to ask for this section. I find this section honestly really confusing reading it as a student for the first time because this is how it's presented. You get that formula, then you get that formula, they call it like equation 5, 6, then you get that one, that's equation 7, equation 8. We have to fill in the dots of how these are coming together and what is ds in the first place. It's a finicky section for those reasons. So I appreciate all the questions. Just a recap. If you rotate about the y-axis, excuse me, let me try again. For the recap, if you rotate about the x-axis and you have a function of y, then y goes in here because of the x-axis. But if there's limits on x, you need the actual function of y down here. Turn it all around a little bit, rotate about the x-axis, y still goes in. But if your limits of integration is with respect to the y variable, you now must have a dy here. A y is not a function of x. It's playing the role of just an ordinary variable this time. Definitely kind of wild though.
If we had the other way, for example, if we had x as a range for x,
Yeah,
we just find the range for y and use this equation.
yeah. If we had values for x, we'd plug them in here,
Here's y, so we can
solve for y. Exactly, yeah.
So, right coordinates when they're being repeated around the x-axis.
Let's see. Not always. So say, for example, this one right here rotated about the x-axis gave coordinates for the x variable itself. So the actual limits of integration will always depend on is y a function of x? You'll have values for x in your limits of integration. Or if you have limits of integration for y, the situation's changed. X is now a function of y instead. So it is confusing. Everything goes backwards in a real sense with that.
You could theoretically express the same equation, the problem, the other way.
Absolutely. I think that's what Rajab was saying. You could take this function right here, solve for y squared. It'd be something like y squared equals x minus, oh, hang on, x minus 1 divided by 2, then you would square root it. You'd want to take the positive root. Then the next thing you want to do to get values for x, you would just put in, say, y goes from 1 to 2, put a value of 1 right here. You get your value for x, put in a value of 2 here, get your next value. So you could rechange everything if you'd like and make it work out. What the author is doing with these kinds of problems is kind of just trying to point out that if everything's more convenient with x being solved, you might as well stick to this because the work is essentially the same. You're just changing the role of x and y, but it has ramifications where y suddenly does do different things. It's now just simply a variable. Lots of wild stuff with this, but you're absolutely right. You could retune the whole problem to do it like example 1 for sure. Other questions at the moment? Okay, well, we got through that part. That's always the challenging portion, running through the square root. Now to do the problem in total, really not too bad. We'll say that the surface area S is a definite integral of, let me put in the 2 pi here, just so it's less of a distraction. Integrate from 1 to 2 of just y. Again, we didn't have a function of y, so that's playing the role of a variable. multiplying the square root of 1 plus 16y squared. Then a dy, since we have limits of integration on just the y variable now. And now for that integral, really not too bad. Just a good u substitution would do the job. So let's run through it. We could set u to 1 plus 16y squared. I think that's a sensible choice because the differential du gives us 32y dy. And we just so happen to have y dy. So depending on how you like to do it, I usually do divide the constant out and call this 1/32 of du is y dy. So that's going in for the blue highlighting here. Then, well, I guess it's a u substitution. You don't always have to take this approach, but you'll often notice the author almost exclusively does this. Let's change the limits of integration. Again, it is your choice. There are values for y, so y goes from 1 to 2. Keep it in this order so I don't accidentally mix them up. That will imply the new variable u goes from, let's see, plug 2 here, it's 4 times 16, 64, plus 1 for 65. Next, plug a 1 inside there, that's 16 plus 1 for 17. We're going from 65 to 17 on this integral then. So integrate from, or take 2 pi and integrate from 17 to 65. Let's do the substitution in blue. Y dy is a 32nd of du. Here's 1/32, just multiplied in. Du, sorry, say again. Oh, weird. Thanks for spotting that. That's a weird mistake. That was a 65 up there. Those copiers will get you. Thanks for spotting them. So we've got a du there. And finally, the root we could just write as a power of 1/2 if we like. And now it's a variable u. So that's the integration we have to do on this thing. It's pretty much just pi 16ths, a little bit of space. Add 2/2, that's now 3/2. So we multiply by 2/3. This is the part that feels almost exactly like the last example. Evaluation goes from 17 to 65. And I did that again. That's weird. I don't know why I wanted 16 there. Tried it again. 65. That's a hard problem to get in. I'm not too sure why, but let's keep on going. Finally, this is pi 24. Look, 65 inside here, you get 65 to power 3/2 minus 17 to power 3/2 on the lower limit of integration. You're totally fine to stop right here, but if you like to match up the back of the book answers, it ought to be written this way. Pi 24ths multiplying 65 root 65 minus 17 root 17. Honestly, I hate it. I think this is a little bit more simplified to visualize, but if you're trying to get to fractional exponents, or excuse me, take out the fractional exponent here, put in a radical sign, that's the steps you would take. Well, any questions at all, folks? Running through that one? Okay, the oddity about this problem was not that we're rotating about the x-axis. That's the more routine problem. It was the fact that they gave us a tough problem. If we try to make that formula work like the original formula, you do have to solve for y, you do have to find new limits of integration, but this is now just a shortcut. You could just work it out this way and get the same exact value using our second formula in the notes. So let's try it all out again. This is the last example for these notes. Not too many homework questions along these lines either, since this is kind of a one-dimensional kind of section, just surface areas after surface areas. They give us a new curve, y equals a 4th x squared minus a half natural log x. We have a domain on x, so nothing weird going on with our setting up our integral, except we're rotating this one about the y-axis. So there is a change there. If this is the whole thing we saw, we didn't even look at a graph, we could already tell that this is going to be set up this way. Surface area goes from 1 to 2. Those came from here, the limits on x. Then it's going to be 2 pi. And what would you put here next? It is x, good call. The different rotation, this time about the y-axis, produces an x right here. Then square root 1 plus dy dx squared dx. So that's our formula to navigate through on this one. But just because we can, just to emphasize it's helpful in the homework as well, let's plot the function and just see if it even makes sense. So y equals 1/4 x squared minus 1/2 natural log x. That's a pretty interesting curve, but we're taking it from 1 to 2. So it gets kind of reduced a little bit. It's just that now. We're taking that shape, rotating about the y-axis. So graph about like this should do the job for us. We try to make it more symmetric. If this was a real exam question, I'll produce graphics like this just to help out in case, again, this helps you visualize the formula. So going back to this, if we were to draw the rest of it, well, let's not do that. Let's just make it a simple drawing. X is going between 1 and 2, so you pick just some random location for x. The moment you do that, you get a line segment that goes like this. That entire line segment is rotated about the y-axis, and so you get something along these lines. One huge little thing going like that. That's a horrible drawing. But the punchline is, if you look at this from the y-axis looking down, what you needed is that radius. It was x, meaning the circumference is 2 pi x. And that's why it comes together in this way if you rotate about the y-axis. So this could be a challenging problem, but this x again could give us some leverage. Sometimes use substitutions work, but we'll see what to do in this case. But that x is just a variable. We don't have to put anything else in. We're just going to work out this stuff next. So going through the mantra, let's do dy dx to start. This will give us 1/2 x when we differentiate that first term. Here, this will be minus 1/2x in that kind of way. So that's dy dx. Next step, we square the result. This is the part of the notes where, again, it might feel like deja vu once more. Squaring this term would give us a 4th x squared. Multiplying here to here, that turns into negative 1/4. Minus 1/4 gives us a total of negative 1/2. Last thing to do to FOIL this out is multiply that by itself to get plus 1/4 x squared. So that's how it stands. We build it up by adding 1 to that result. So 1 plus dy dx squared is 1 plus 4th x squared minus 1/2 plus 1/4x squared. So next, we'll combine our like terms and get a 4th x squared plus 1/2 plus 1/4x squared. Plus 1/2 is taking the 1 minus 1/2 of it. My claim is that this automatically factors. Any volunteers for what should go inside? Anyone happen to see it in Zoom? What the first term should be right here? Exactly. So we get 1/2x to start. It's got to be a positive sign in the middle based on the form of our trinomial having positive signs. And same trick on this one, 1/2x. Or hang on, I've got my x in a weird spot. Let me fix that. I think you said 1/2 x.
Yeah.
And then 1/2x. So that's the factoring of that. And there is some big hints on this. We saw, this is the 3rd time this kind of algebra came up. But observe, those should be about the same. Only difference is the sign in the middle whenever algebra starts going in this kind of direction. This is pretty common, by the way, only because it's actually, again, not easy to come up with a lot of these examples that work out just right. And so our authors seems to have come up with a process for inventing problems in a regular way. But then the algebra becomes predictable after you do it 3 or 4 times. It's usually stuff like this. Not every time, but finally, we're putting a square root on everything. So if we did that right here, here's what it would look like. Gigantic mess at the start. But then finally, right here, we have a mathematical miracle. It's just 1/2 x plus 1 over 2x. No parentheses required. So that gets us across the nasty part of this, sorting out the root. Now we just have to finalize the problem. So we have a surface area equals, I always like to take 2 pi out. That's a personal choice. You don't have to. We're going from 1 to 2 of x times 1/2 x plus 1 over 2x dx. And that's a pretty friendly integral based off the things that we've seen in class. You'll notice chapter 7 is like the worst case integration, but the integration cools down a lot in chapter 8, 9, and so on. So continuing through this, it's 2 pi. Integrate from 1 to 2 of 1/2 x squared plus 1/2. All I've done there is distribute this x into the group to the right, so we can get a clean antiderivative going term by term. So now it's 2 pi. Big parenthesis, first antiderivative will be 1/6 of x cubed. Then this one's not so bad, just throw an x on it. 1/2 times x. All evaluated from 1 to 2. And this is the arithmetic side of the problem. It's now 2 pi times. Putting a 2 here gives us 8/6. Putting a 2 here will give us a plus 1. Now plugging in 1 just gives us a 6 plus 1/2. And let's sort this out. 6 plus 1/2 is really a 6 plus 3/6. So we get a 4/6 or a 2/3 from that parenthesis right there. So this is turning into 2 pi multiplying. We might as well reduce that down to 4/3. Plus 1 minus, that turned into 2/3. And it keeps on going. Let's see when this terminates. Next step, it's 2 pi. We have a 4/3 minus a 2/3, so it's back down to 2/3. The one we can write in as a 3/3. So it's sorting itself out. Now it's 2 pi times 5/3. Finally, that just gives us an overall quantity of 10 pi divided by 3. We didn't have any units on this, but if you really want to think of this as an applied problem, you can always say units squared. Not required at all, but it's just a good reminder of what you calculated, an actual surface area to whatever this thing would generate, some weird band again. Well, any questions at all, folks, with running through this one? Okay, so lengths and surface areas, those are really, well, we still call them applications. It's in the application section, but they're just curious math problems. They do have big applications, but our book didn't actually have very many examples to support them, unfortunately. We're going to go into section 8.3 next, where we do have a lot of really practical and pretty cool examples, looking into hydrostatic force and to centers of mass. It's just a bunch of integration, it turns out. Those integrals will get a little bit involved, but no weird algebra like this, more routine kind of integration like chapter 7. Well, this will be our stopping point for the night, folks. Any last questions before we call it a night officially? Okay, as far as the work goes, assignment number 8, this one is now considered assigned. I put a due date on October 2nd on this one. Even though we finished it today, I just feel uncomfortable putting a due date for 2 assignments on the same day. That just feels like a bit much. So these sections aren't too large. There's not too many crazy problems. I still feel like this is a good amount of work because they're just longer problems as well. This is a tricky section, but for every one of those problems, you can go to these notes and find something similar to get you some motivation to get started. But don't hesitate to email me if you have any questions. I'll be happy to help out. We'll see you later, folks. We'll come back to section 8.3 on Wednesday's class. Yep, you betcha. One thing I forgot to say is if you're in Zoom, but you have a hard copy of your exam, don't hesitate to email me and say, could you scan that over? No problems doing that for you. I'd be happy to help out.